Hello, my name is Sigve Hovda. I am professor at NTNU, and I am also attached to the BRU21 project. A few years ago, we started a company named Computerwell, and I am CEO in that company. Today, I'm going to tell you how we think our technology can make you drill faster, further on every run, and also make straighter holes. This is a decade of research, and really what we've been doing is made a digital twin of the drill string. So we have molds for the drill string, we also have molds for the hoisting system and the heave compensation system, the top drive, and we also have a hydraulic mold so we know the pressure everywhere in the drill string. And we have a bit rock interaction model, and recently we also created a mold for lateral vibration. So what we have is a stiff string model that is dynamic. Let me explain a little bit more about the technology. The input is basically the surface parameters, usually, and also the drill string, and we treat the rock strength as unknown, and also the friction in the hole as unknown, and also the hole quality. What we do is make many simulations with different parameter setting of the unknowns. And then we get many simulations that we compare with the measured hook load, torque, pressure, and also vibrations downhole. And together we find, we actually predict the unknown parameters because we pick the best one that fits the data the best. Let me give you an example of drilling in an interbedded formation. In the middle you see the weight on bit. And normally that's just a curve, right? But in this case, we actually see that the green one is the force that's acting on the cutter, while the cyan color is the force that's acting on the wear flat, only creating friction, right? When we look at the curve to the left, then we see that a greater portion of the force that's acting on the cutter, the green one, right? That's a greater portion because then it has a different direction. And we also see the cyan color, which is on the wear flat. And then we also have two other torque-related forces, which is just friction in the hole and also friction against the fluid, which is the blue one, and the friction on the wall is the green one. All of this information together, we actually predict the hardness of the formation, which is the magenta-colored curve to the right here. And we see that how it fluctuates there, and we get that into numbers that make sense and are comparable to what we believe is the confined compressive strength of the formation. So what we think we can do with all this is we can say something about how hard the formation is, and more importantly, we can also say something about when the bit is actually getting dull. Because a dull bit is having less torque response to the weight on bit than a sharp drill bit has. And since we're modeling the whole process, we think we can distinguish all this and try to figure out when our actually bit is getting dull. The consequence of this is that you can drill further on every run because you know when to pull out. When the bit is dull, you do that quickly. And if you think your bit is dull, then maybe you have a longer life into it and you can drill further on it. Another thing is we think we can drill faster. How can we do that? Well, we want to challenge the conventional idea that you get the drill bit and it's certified for a certain amount of weight on bit, like 15 tons, 10 tons, or something like that. We think that this can be a lot higher because we have this knowledge about how dull the bit is and also all the forces acting on it and also the heat being generated at the bit because we know something about the friction that's created. So we think that we can help. We don't say we can help you drill faster all the time, but when there is a chance to increase your weight on bit and thereby drill faster, you should do it. And then we can probably say when you should be more careful about it. So this is how we think we can drill faster and further on every run. In the near future, we also want to say something about how you can drill straighter holes. And I think the big challenge is how to drill the stringers. And usually you come into them with an angle like you see here, and then you get all these vibration. You get torsional vibration because there's uneven force distribution on the bit, and you also get lateral vibrations. And we think that And we have a model for all this. So we think that in the near future, we're going to be saying something about how you drill these faster. And we already are predicting the stringers. We feel quite confident about predicting them at the bit. So that's our mission. And let me just show you the team. You know, Asbjørn and Magnus Jare are computer scientists, and then me and Magnus Hallaråker is on the modeling side, and then Sigbjørn and Tim is mostly on the drilling side. Thank you.